Hello and welcome to this video about heterocyclic chemistry. Here we'll be looking at nomenclature of heterocycles. So heterocycles are cyclic compounds having at least two different elements within the ring. But very quickly what we can see is this covers a vast array of different molecules. So in order that we all know what each other are talking about, it's important to come up with a system of rules for naming these molecules. In fact, there are three systems which are in play as defined by UPAC, the International Union of Pure and Applied Chemistry, who is in charge of this kind of thing. The first set of rules is the Hans-Widman nomenclature. This is a logical system by which you can name various different heterocycles. However, some of the older heterocycles which are very prevalent, keep their older, more traditional names. Finally, some heterocycles are very complicated, and for those we need a backup system which involves naming the carbon framework and then describing where the heteroatoms are. So, to start off with, looking at the Hans-Widman nomenclature, in order to name a heterocycle, we really need to know three different things. We need to know what are the heteroatoms present in the ring, how big is the ring, and how much saturation, how many double bonds are there in the ring. If we're going to try and make a name out of this, starting off with the heteroatom, we can use each element to give us a prefix for the name. So oxygen gives us oxa, selenium gives us selena, phosphorus gives us phosphor, arsenic gives us arsa, and silicon gives us sila. These are kind of obvious ones. For some of the other ones, such as sulfur and nitrogen, are a little bit less obvious. Sulfur gives us thia, and nitrogen gives us aza. Although, as you'll see, because nitrogen heterocycles are so important and prevalent, you'll see that sometimes instead of aza, the prefixes imid and pir are also used. If we have more than one heteroatom in the ring, then we can use multipliers to describe the system. So one nitrogen, for example, gives us an aza molecule, but if there's two, it's a diaza. If there's three, it's a triaza. If there's four, it's a tetraza, etc., etc. If there's two different elements in the ring, then we just combine the two prefixes. So if there's a nitrogen and an oxygen, it becomes an oxaza. If there's a sulfur and an oxygen, it becomes an oxathia. And if there's a phosphorus and an oxygen, it becomes an oxaphosphor. Now, the order in which we combine the names is which element is furthest to the right, so has the biggest period on the periodic table, followed by which has the smallest row, so near furthest to the top. Next, we need to look at the size of the ring in our heterocycle. And each size is given a different prefix. And these prefixes are mainly derived from the Latin and Greek for numbers. So for example, three-membered rings are IR, and that's from the letters in tri, as in triangle, but reversed. Four-membered rings are ET, from tetra, for example, tetrahedrons. The 5 and 6-membered rings don't follow the rules, so 5 is OL and 6 is IN. 7-membered rings are EP, that's from hept, like a heptathlon. 8-membered rings are OC, from oct, like an octopus. 9-membered rings are ons, from non, as in nonagenarian, somebody who's 90 years old. And 10-membered rings are ek, as in deca, as in a decade. Finally, to make the last part of our name, we need to figure out how many double bonds there are, how much saturation there is in the molecule. If the molecule is completely saturated, then we add the suffix ane, ane, to the end of the name, so that 3-membered rings become iranes, 4-membered rings become etanes, 5-membered rings become olanes, Now 6, we lose the IN prefix for most of our rings, so they're just anes. 7 are epanes, 8 are ocanes, and 9 are onanes. In the unsaturated version, so this is the version with as many double bonds as is possible, instead we use the INE suffix. However, again there are some exceptions. So we start off and instead of the INE, we use ENE. So 3-membered rings are erenes. 4-member rings are eats, so just an E instead of the INE. 5-member rings are oles, so oles instead of olenes. 6-member rings are just enes with no prefix. 7-member rings, we go back to the rules again, so it's epenes, ocenes, and onenes, and essenes. However, nitrogen gives us some problems. So for nitrogens, we use a very slightly different names, and that are names often with an extra -ide in the name. So for 3 members, it goes instead of irane to an iridine. For 4-membered saturated heterocycles, it's an etidine for nitrogen. For 5-membered saturated heterocycles, it's an olidine. For 6-membered heterocycles with nitrogen, it's an inane. And finally, for 3-membered unsaturated heterocycles with nitrogen, it's an irene, so spelled slightly differently. Looking at a set of heterocycles here, we can start to see how we can name these different ones. Our first one contains a nitrogen, so it's an as. It's a 3-membered ring, so it's an ir. It's saturated with a nitrogen, so it's an idine, and that gives us an aziridine. Our next one is an oxygen-containing heterocycle, so it's an ox. It's a 7-membered ring from heps, we get EP, so that's an oxep. And again, it's completely saturated, so we get an ane, so oxipane. The next example contains a nitrogen, so it's an as. It's an 8-membered ring, so we look at oxa or OC. And now, because it's completely unsaturated, it's an ENE, which gives us an azocene. Moving on to our 5-membered heterocycle here, we have 3 nitrogens. So because there's 3, we can say tri. Nitrogen is as, so it's a triaz. And our unsaturated 5-membered heterocycle gives us ol. So this is a triazole. And you can see in triazoles, there are 2 different ways to put the nitrogens around the ring. And we can differentiate those by using numbers. So 1, 2, 3, where the nitrogens are next to each other, and 1, 2, 4, where there's a gap. And we'll see more about numbering heterocycles later on. Moving on to the second row, we have a 6-membered ring containing a sulfur, completely saturated. This is a thiane, so thia for sulfur and ane for our 6-membered saturated molecule. Now we have 2 heteroatoms, remembering to start on the right-hand side, top of the periodic table. That gives us an ox for the oxygen, followed by an as for the nitrogen. It's a 5-membered aromatic heterocycle, so that is an ol. So this is an oxazole. Similarly, instead of ox, now we have a sulfur, so we switch from ox to thia. That gives us a thiazole. This is again another ol because it's a 5-membered aromatic heterocycle. There is 4 different nitrogens in there, which gives us a tetrazole. There's only one way to organise this, so we don't need to look at the numbers this time. And for the last one, again it's an ol, and the prefix for arsenic as well. You can figure this one out by yourselves. But we have some problems. If we look at the bottom row of this, well, the names that we come up with here, so an azinane, a diazole, azolidines, don't actually correspond to the names we use for these heterocycles. Furthermore, we have some complicated heterocycles down the bottom, which we struggle to name in this system. So what do we do? Well, the ones on the bottom left all fall into the category of heterocycles with retained names. A lot of these are so important and well known, they actually predate the heterocyclic nomenclature system developed by Hans and Wittmann. So there are things like pyrrole and furan, which are known in ancient times. So pyrrole, again, this goes back to the element prefix. So actually the ol is correct, right? We have the right OLE for a 5-membered aromatic heterocycle, but instead of AZ, we use pyr. So this is a pyrrole. Furan instead of an oxole, that comes from the fact that it's made from bran or furfur in Latin. We have a thiophene instead of a thiol. We have a pyridine. So again, we can see instead of as, we're using the pyr prefix. So we have a pyridine instead of an azidine, a pyran instead of an oxine, a thiopyran instead of a thiene. Pyrrolidine, again, is another one of our preferred names, as long as pyridine and morpholine. When it comes to heterocycles containing nitrogen and then another or heteroatom, then again some of the names are retained rather than using the systematic approach. So instead of calling the 2 nitrogen containing 5-membered aromatic heterocycles 1,3 and 1,2 diazoles, instead we play around with our nitrogen prefixes. So the 1,3 diazole now becomes an imidazole, and the 1,2 diazole becomes a pyrazole. Now, oxazole containing the nitrogen and the oxygen, well, that follows the rules, and it's actually a 1,3 oxazole. But instead of calling the 1,2 oxazole a 1,2 oxazole, that's called an isoxazole. And a similar thing happens to our 6-membered aromatic nitrogen-containing heterocycles, where we use 2 different versions of the prefixes for nitrogen to make the system. So the ene part gives us the correct name, but our system with the 1,2 nitrogens next to each other becomes a pyridazine, 1,3 is a pyrimidine, and the 1,4 is a pyrazine. But that still doesn't help us out with the 2 at the bottom right. Now these are fused heterocycles, and actually when it comes to fused heterocycles, so these are a furan fused to a benzene, well, we can just fuse the 2 names. So a furan fused to a benzene becomes a benzofuran. A furan fused to a pyridine becomes a fluoropyridine. The order in which we fuse the names means we take the biggest cycle that contains the most heterocycles, and that comes last. Again, there are some fused heterocycles that have retained names. So instead of a benzopyrrole, we have an indole, and instead of benzopyridines, we have quinoline and isoquinoline. Now the final system for very complicated heterocycles, and heterocycles that contain more than 10 atoms in the ring, we have a system whereby we use the all-carbon version. Now, the all-carbon version of names can cope with almost any different structure that has been conceived, and therefore is extremely robust. And therefore, what we do is we name the all-carbon version, and then we'll just describe where the heteroatoms are. So in a very simple example, benzene, instead of becoming benzene, is an azobenzene. So it's a benzene with an aza, a nitrogen, in the ring. Of course, we don't call that azobenzene, we don't call it azanine, the Hans-Richtman rule, we call it pyridine from its retained name. When we talk about heterocycles, it's not just the heterocycles themselves, but substituents around the ring that are important. And therefore we need a system of numbering that tells us where things are. Now, the system is simple. What we do is we start from the heteroatom that has the biggest period or the smallest row, so the same system as we used when we had the multiple heteroatom containing molecules, and we call that one number 1. And then we number around the ring consecutively. Now, if there's more than one heterocycle, we want to number around so we get the next heterocycle, like in oxazole, becomes the lowest number. So it is a 1,3 oxazole and not the 1,4 oxazole. If there are 2 nitrogens in the same ring, like in an imidazole, the one which is most saturated has the lowest number. So the NH is N1 rather than the other one, the N3. We also, when we do numbering, we want to try and get any substituent to be the lowest number. So in the first example, where we have a 3-methylpyrrole, that's fine. But in the second one, we've kind of drawn a 4-methylfuran. Well, we don't really want that. It's much lower number if we call it a 3-methylfuran. It's the same compound. Now, when it comes to fused molecules, we use the same system. We start from the heteroatom, we number around the ring. But what's important here is that we miss out any of the ring junction carbon atoms. So you can see here quinoline starts off, nitrogen is 1, the carbon next to that is number 2, the carbon next to that number 3, then number 4. Now the next carbon round is at the ring junction, so instead of being called 5, that becomes 4A. We skip that one and we carry on 5, 6, 7, 8, and then the last one becomes 8A. The exact same system can be applied for benzofuran. Finally, just because there wouldn't be a rule unless there was an exception, one of our retained named heterocycles, so our isoquinoline, doesn't use the same numbering as the system where we'd expect to start the number at nitrogen being 1. It uses the same numbering system as quinoline. So be careful with this one. The rest of them are all fine. So finally, we need to think about what happens when we have partial hydrogenation. Our system tells us how to name compounds like pyridine, which are fully aromatic, or like piperidine, which are fully saturated. So what happens in the middle? Well, here we just use the numbers to describe where the hydrogens have gone. So for example, if we take pyridine and we put 2 hydrogens on, well, there's 2 ways we can do that. We can put the hydrogens at the 1, 2 position or the 2 and 5 position. So these molecules become dihydropyridines. We can go one step further and we can get tetrahydropyridines. Now obviously, when we go all the way to the next stage, we get a hexahydropyridine, which we call a piperidine. We can do the same thing with furan, where furan starts off as a furan, then goes on to a dihydrofuran, again using the numbers to describe where the hydrogens are, finally getting tetrahydrofuran, or THF. So I've tried to walk us through the different systems used for naming heterocycles. I've also compiled a list of the most commonly encountered heterocycles in the handout, if you prefer just to learn them, which is a perfectly acceptable way. In summary, there are 3 systems for naming rings. We have the Hans-Wittmann nomenclature, which is a logical system based upon the elements present in the ring size, and how saturated or unsaturated this molecule is. We can see that also helps us name fused heterocycles. But some of our older heterocycles, some of the more important ancient heterocycles, keep the original names, the ones that they had before Hans-Wittmann nomenclature came along. Finally, when things get too complicated, we have to use our carbon framework substitution nomenclature. We've also seen how we can refer to the different positions on heterocycles by numbering, and what happens when we have a partially saturated heterocyclic system. Thank you for watching. I'll see you next time.